All right, again, we're looking at a Khan Academy screen because if you're one of my students, I'm about to assign this to you. But I like it because it's a good way to talk about how to move from word problems, word descriptions of a situation into an exponential function. And to remember, an exponential function is when the change that happens each time period is by a percent or a factor, like it is half as much as before or twice as much as before, or it increases by 5%. These types of changes are going to lead us to exponential expressions or exponential functions. So if you look at this first example, a manufacturing plant earned $80 per man hour of labor when it opened. Okay, each year the plant earns an additional 5% per man hour. So that's part of our key right there. It says an additional 5%. So the change that's happening each year is that it's more by 5%. So our multiplier, our rate of change, is going to be, we had 100% of what we started with plus another 5%. So that is 105%, which as a decimal, like percent means over 100. So it's going to be 1.05. So each year I'm multiplying again and again and again by 1.05. What about the beginning of time? What happened at the very beginning of this whole situation? Well, when they first started, it was $80. So eventually you won't need to make this table, but like, let's go ahead and consider over time. T, as they've said here, is the number of years after it opens. So when it very first starts, time 0, beginning of the whole time, we have these 80 man hours. And then every year after that, we have to multiply that 80 by 1.05. So after 2 years, I have the original 80. It already increased by 1.05, and I multiply it again by 1.05. And you'll notice a pattern here that each time the number of times I am multiplying 1.05 is the same as this number. So in function form, it is the original 80. That's my initial value. My rate of change, 1.05, to the power t. So here for Khan Academy, I'll write 80 times 1.05 to the power t. This entire video is about exponential word problems, so it's basically the same thing we see here. Mapilla writes a series of novels. She earns $75,000 on her first book, and her cumulative earnings double with each sequel that she writes. So here, our rate of change, it's doubling. How much does she have? Every time she has twice as much as she had before. Double is like 2 times. So also I want to highlight, what did she start with? The first book was like this. And I will make the table. At some point, you will be able to just know what's happening here with the table numbers, but until you do, it's a good idea to write out the first few numbers of books in this case, or numbers of years, the first few values. So that's n, and then over here, they're deciding to call the output e of n. Okay, so does 0 make any sense? She's written 0 sequels. I guess, because if she's written 0 sequels, she's just written the 1 book. So if she has only 1 book written, her earnings are 75,000. If she writes 1 sequel, then she has the original 75,000 times 2. If she writes another sequel, she has the original 75,000 plus the already once doubled, and then it gets doubled again. So again, we start to see the pattern. The question is, how many times am I doing this multiply by 2? It is the same as this value, which means my expression is e of n equals, I'm always having this initial amount. I am then multiplying by 2. And how many times am I doing it? N times. The format here is a little bit different because I needed to go find specifically the type of question I was looking for. All right, so we have Tsang Li tracked the size of the bear population in a nature reserve. The first year, the population were 1,000 bears. So 1,000 bears in the first year. Sadly, the population lost 10% of its size each year. So they lose 10%, which means my multiplier, there were 100% of the bears, but then I lost 10% of them, which means I only have 90% left. So every time period, which in this case is a year, each year, I'll be multiplying the population by 0.9. Let f of n be the number of bears in the reserve in the nth year since Tsang Li started tracking it. So as per usual, we're going to go ahead and make a quick little table. Our letters here, we have n for the nth year, and they've chosen to call it f of n, which is our population of bears. So in the first year, we know already, they say, in the first year, there are 1,000 bears. In the second year, we have those 1,000 bears, but then we multiply by 0.9 because it's decreased by 10%. In the next year, so in the third year, we have the bears from before. And then again, it's decreased by 10%, meaning there's 90% of them left from the previous year. And so we start to look at the pattern. How many times have I multiplied this 0.9? That's twice. And I want to compare it with this number here. That's a 3. It's not the same number. The one on the right, this one is one value smaller. So let's look at one more row. Say we're looking at the fourth year. So I have the original 1,000. I have from the third year this many bears. And now again, I multiply the population by 0.9. So here, there are 3 times that I'm multiplying the 0.9 for the fourth year, which means that in the nth year, I'll have this 1,000, and I'll have a bunch of 0.9s multiplied together, but how many of them will there be? There will be n minus 1 of them. The number of times I multiply the 0.9 is 1 less than the number in the number of years column. So then f of n equals the 1,000 that I had in the first year, my multiplier of 0.9, and the exponent this time is n minus 1. So that will be my exponential function. This exponent here is different this time than the previous times, and it's simply because of where my table started. So at some point, you'll be able to do it without the table. It should become obvious whether it's n or n minus 1. But until it's obvious, go ahead and make the table and see where it starts. If you start at 0, you're probably going to have the exponent that's just an n. And if your table starts at a 1, you're going to end up with an exponential function that has an exponent of n minus 1.